Okay, it looks like we're recording. So we're going to finish up chapter 3 today. And we're going to focus on a couple of things with combining capacitors and inductors and doing a little bit of work to show the combination of the two. So we'll start off with capacitors. And you may recall this from your classes with John Allen, perhaps. But if I have, whoops, that's the wrong color. Where's my white? White, where are you? Where's white? I guess I can't change that to white. I don't know why. Bottom right corner. Is that white? Looks like gray to me, but okay, we'll try it. So let's say that I have two capacitors in parallel with each other, C1 and C2. Remember how we talked about trying to make equivalencies of circuits or elements? So it would be really good to figure out how we can put capacitors in series or in parallel, either one. Well, what is the equation that we use for governing capacitors? What's the equation that we use? We like two equations, right? What are they? And then we also have the integral of our voltage. So we have the integral of I C of t dt 1 over C equals the voltage here. So we can use one or both of those equations to figure out how to simplify this particular circuit. So let's go ahead and let's actually start to write a KVL equation. So we'll call this I in. And then we're just going to use these two circuits. So we're doing the Thevenin equivalent, if you will, of just those two. So we have IC1 and we have IC2. So I in of t by KCL is equal to IC1 of t plus IC2 of t. Right? Those three are equal to each other. But we've already said we have this equation over here. So let's substitute. This becomes C1 dV C1 of t dt plus C2 dV C2 of t dt. Now we just made our substitution based on those equations. And now what we've noticed is the voltage across those two capacitors is just VC. Because it's a common node, it's exactly the same voltage. So that means that dVC1 equals dVC2. So this becomes C1 plus C2 times the derivative of our common voltage. And now we can say, oops, I'm not sure why this is being so particular for me. So now we can say that I in of t is equal to this capacitor here. We'll call it an equivalent capacitance times dVC of t dt, which if you go back to our original equation up here, that's the base governing equation for any capacitor. If I want to solve for any current going through a capacitor, all I need to do is take that capacitance and multiply by the derivative, which is what we've done here. So we can say that an equivalent capacitor, a capacitor that is just here, is going to look like taking my two capacitors and adding them together. So why do you take capacitors that are in parallel with each other and add the capacitance together to get the equivalent capacitance? Because our CVDT equation told us to. It's not because we waved our hands magically and we end up with the correct value. It's because the math tells us that, which is different, right? Because if we have two resistors over here, we know that our equivalent is equal to the product. Oops, can you hear me? Hello, is there a question? No, okay. So it's equal to the product over the sum, which is completely different than how we would go ahead and solve this particular one. So C equivalent is C1 plus C2, which, if you think about it, kind of makes sense, right? Because if I have a capacitor in parallel with a capacitor, how do capacitors work again? You take a plate of metal on one side and a plate of metal on the other side, and you stick an insulator between them, and you prevent the electrons from flowing through. Isn't this basically just saying I have a big plate and another big plate with the same amount of insulation? I've just increased the area of the plates, haven't I? So in a sense, I've got a bigger capacitor, not a smaller capacitor, because I have more area of plate for charging. Insulation distance hasn't changed. Remember, the capacitance is based on the amount of insulation distance, right? Not distance, but how hard the electrons have to travel through that insulation. So just because I have more plates, I haven't increased the depth of the insulation. So there's nothing that I need to do there. Okay. So that's how I can prove that one. We can also prove this one here. Let's put two capacitors in parallel with each other, C1, or series with each other, C2. This is VC of T. This is IC of T. And we know from our equation over here that VC of T has to be equal to 1 over C, times the integral of IC of T dt. Okay, we have that. We are convinced that that is valid for us and that works for us. So if we can use this equation to make it look, to make this and this look like it, we can do that C equivalency. But let's go ahead and solve for the individual voltages first. So VC1 of T equals 1 over C1, integral of IC of T dt, and VC2 of T, integral IC of T dt. And then we know that my applied voltage is VC1 of T plus VC2 of T, because those are in series with each other. So we're just summing the voltage drops. The voltage from here to here is just the sum of the two voltage drops across the capacitor. So we're going to substitute these two in here, and we end up with 1 over C1 integral IC of T. And I'm just going to drop the dt because I'm trying to save some space. But my integral of IC of T is interesting because it's the same current going through both capacitors. So what that tells me is that these two can be factored out. So I have 1 over C1 plus 1 over C2 times the integral of IC of T is going to be equal to the combined voltage across the capacitor. And if I go back over here, that is 1 over my C equivalent. So my 1 over my C equivalent is equal to 1 over C1 plus 1 over C2. So I'm going to put these under a common denominator, C1, C2. This is C2 plus C1 is equal to 1 over C equivalent. So C equivalent is equal to C1, C2 over C1 plus C2. Is that what you expect? Is that what you expect to see when you have two capacitors in parallel with each other? I mean, in series with each other? That it looks like resistors in parallel, doesn't it? Capacitors in series look like resistors in parallel. Why is it? Because the math works out that way. And it's all based on the fact that it's an interval equation. So this equation is derived based on how you obtain voltages and currents in capacitors. And is exactly what we expect. Also, let's take a look at capacitors, right? I got two capacitors in series with each other. I've got more aluminum, right? Or more, whatever the mylar is, whatever metal that is the ability to store charge. But remember, what I want to do when I have a capacitor is I want to increase the amount of area because it's more attraction. So I want to increase the amount of area that I'm storing my charge. That increases the capacitance as long as I don't make the distance greater. Well, have I increased the area over here? I really haven't, because essentially I only have a plus and a minus down here that is going to jump across. So I haven't increased the area at all, but in fact, I now have two insulating mediums that make up a greater area. So my area hasn't increased at all, but I've just made it harder for those electrons to jump across. So I've decreased the capacitance because it is less able to store energy, right? There's less attraction between those two plates because the insulation or the distance is greater. So you know that you have to, just practically from a standpoint, I have to decrease the capacitance value because it has less ability to store energy. So I'm decreasing the capacitance. Okay. We can do the same thing for inductors. Do you want to do both or just one or the other? Because with inductors, you have the same thing. Either or both, do you care? Do both? All right, let's start with inductors. Parallel, L1, L2. What are the equations that govern voltages and currents in inductors? Anybody? What is the voltage drop across an inductor equivalent to? L di dt. So that's the voltage. So I know that I have a voltage across these two inductors, and I have a current in here. And so I'm going to use this to go ahead and solve for the voltage. So V of t is equal to VL1 of t plus VL2 of t. But VL1 of t is just going to be using this equation. So that's equal to L di dt, L1 plus L2, because this is now L2 di dt. And that current is the same. The di dt is the same current through there. So I can factor that out. And the concept of an equivalent inductor is I have a voltage across it and the same current through it, then this is my L equivalent. So if I say V of t equals L equivalent, di of t dt, then L equivalent is equal to L1 plus L2. So inductors that are in series with each other, you just add them up. Which makes sense because if I look at an inductor as an actual coil of wire, I'm generating magnetic field around that. When I add another coil of wire, it's another way of saying I'm just adding more turns. I'm putting more turns on the wire, so I generate more magnetic field with that same level of current. So I have the ability to do more magnetic stuff with the same level of current than I did before. So its inductance, its capacity to produce magnetic energy has increased. And I shouldn't say magnetic energy, but the ability to create a magnetic field, maybe is a better way to say it, has increased. So just from a practical standpoint, you may perhaps be able to see that. Now let's look at some in parallel. And in this case, we're going to go ahead and we're going to have to do the opposite. So it's L di dt, right? So we have I of t in an inductor is 1 over L, integral of VL of t. So again, if I have the voltage and the current of a bunch of inductors that are in series or in parallel with each other, it doesn't necessarily matter. It's going to work its way out on the wash. And so what I can do is I can say I of t is equal to I1 of t plus I2 of t. And I use this equation now. That's 1 over L1 integral VL of t plus 1 over L2 integral VL of t. Recognizing that the voltage VL of t is the same for both inductors allows me to factor out the 1 over L1 plus 1 over L2 times the integral of VL of t. So my 1 over L equivalent is equal to 1 over L1 plus 1 over L2. Exactly what we expect to get. Now for the inductors in parallel with each other, I'm generating some magnetic field for a given level of current. When I have an inductor next to it, now my current splits off, right? So I've got a certain amount of current, but it's reduced. And so the amount of magnetic field is determined by the number of turns of wire times the current through it. And as long as these are going in the same direction, I'm not really adding any more magnetic field. I'm just basically having a magnetic device that sort of doesn't really amplify it. It just provides a path. So I'm not creating magnetic energy from that one. I'm just continuing to do more. So I'm not doing any more work with that. I've just decreased the current. So having two inductors in parallel actually decreases the amount of energy or magnetic energy that is transferred. Exactly what we would expect. Okay. So let's see. I want to get into. Well, let's just summarize. So capacitors are opposite. Resistors and inductors are the same as resistors. So what that means is when resistors are in series, becomes R1 plus R2. R1 in parallel with R2, we have the product over the sum. So you're going to work in the opposite direction. So inductors are add them in series just like resistors, put them in parallel just like resistors. For capacitors, do the exact opposite. If they're in parallel, add them as if they were in series. If they were resistors in series, and if they're in series, add them as if they're in parallel. Okay. Questions on that? Any questions? Because we can use this if we want to. We can use that to give us some help with voltage divider. How do you think voltage divider is going to work? How is voltage divider going to work for a circuit? Any thoughts? Well, if I'm looking for VC2, how do I write an equation for VC2?
Would it be like a normal?
Go ahead.
Oh, okay. I was guessing something different.
Okay.
I thought it was like the normal voltage divider rule where it's the one you're not going across times the, oh, that's resistance though. Never mind.
Well, let's try it. Yes, sir.
If capacitors work opposite to resistors, wouldn't you see source voltage over C2?
If capacitors work, you'd see source voltage over C2. The source voltage is across both.
Right. If they act like they're in parallel, then the thought of the voltage stays the same in a parallel circuit with resistors would mean that the voltage would stay the same in series with capacitors, maybe.
Well, let's take a look. That's a good question. Let's see what the answer is. So we're going to go ahead and just solve for our voltages here and see if we can write an expression for our voltage divider. So our VC of T equation, is VC2 T equation is 1 over C times the integral of the current. That's VC2. VC1 is also going to look similar, but now it's C1. And now we're going to go ahead and say that my VS of T is going to be equal to VC1 plus VC2. We're just going to add those two up, right? Because now we're talking about a series circuit. Now, we're also going to assume that we don't know what the circuit is on the output, so we're looking at Thevenin equivalence. So we're just pulling all the elements out there. So we'll solve for the open circuit voltage across that element, which means that the current through here is just going to go through these three. It's just going to be basically a loop circuit, a loop current. So what that tells me is that this current here, I of T, is the same in both cases. So I can make that substitution is equal to, let's see, 1 over C1 integral of I of T plus 1 over C2 integral of IT. And now we're going to go ahead again and factor out. So I have 1 over C1 plus 1 over C2 times the integral of I of T. So that's all well and good, but I'm looking for a ratio, right? So voltage divider, if you remember, voltage divider is for a resistor. Let's just do a resistor. So VR1 equals the applied voltage times R1 over R1 or R2 plus R1. So I can set up a ratio, which is VR1 equals V applied R1 over R1 plus R2. So what I'm doing is, yes, sir.
You mean VC2 there, VC1 plus VC2?
VC2 here, yes, thank you. Oh, yes, that should be VC2, yep. So what I'm saying is I'm just trying to set up a ratio of my output voltage to my applied voltage and see what I get. This is my applied voltage right here. My output voltage, VC of 2, is, I don't see it up here. So my ratio becomes VC2 of T, that's my V out, divided by my applied voltage, is equal to 1 over C2 integral of I of T all over 1 over C1 plus 1 over C2 times the integral of I of T. So I've got my ratio set up, and now we're going to just check voltage divider. Well, the first things we should be able to see is those two will cancel out. So what we have now is 1 over C2 divided by, we're going to have a common denominator. So C2 plus C1 over C1 times C2. Invert and multiply, I have C1 C2 over C2 times C1 plus C2. Cancels that out. So what was the statement Adam made at the beginning? I want the output voltage to be C2 across C2, but look at what capacitor I'm using. I'm using the C1 capacitor, just like what we were doing if we were going to do the case for current divider rule. The current divider rule says to use the not the one of interest. So again, this is just more where we're using the elements that are not of interest. We're still using a series circuit, but at this point, we're looking at the elements that are not of interest. So you're going to have to kind of flip your thinking a little bit, because when we talk voltage divider rule, you can't just say categorically that that works every time. If you deal with capacitors, it changes things a little tiny bit. It makes it a little bit more interesting to think about. Okay. So again, capacitors are a special case where you can't just use all the standard rules. All right. Let's do voltage divider rule for inductors. Should we pause a moment to let you try this one? You want to do a little math in class? Anybody? Interested? Not interested?
I would rather have you like walk us through it, honestly.
Okay, sure. All right, so we're going to do the exact same approach. But in the case before, if we're going to do voltages, we're going to do VL of T equals RL times the derivative of the current with respect to time. All right, that's the first thing. We need to write our base equation to do that. And the output voltage is here, is across L2. So we think if we were going to use our traditional voltage divider rule, it'd be L2 over the sum of the inductors times the applied voltage. Let's take a peek. The first thing we're going to do is write an equation for VL1. And we're going to do the same thing for L2. And again, we're looking at KVL, the KVL. We're looking at Thevenin. We're looking at the equivalence of the circuit to make sure that we get our correct values. So what we're saying is the current through here is the same, because the current is equal to 0 because it's open circuited. There's no current going out of the terminals. Everything is staying inside of the terminals. So now that I have that information, I can go ahead and solve VL1 plus VL2 is L1 plus L2. Now I can factor because the DI/DTs are the same. It's the same current. So L1 plus L2 times the derivative of I of t is going to be equal to the sum of those voltages. But KVL tells us that Vs of t is equal to VL1 plus VL2. So Vs is equal to L1 plus L2 times the derivative of the current through the inductors. So just like we did before, right? We have to set up a ratio, which is V out over Vn, or Vs in this case. So we just need a ratio of those two voltages. So what we're going to do is set up our ratio. And we already realized that V out is our VL2. So that's VL2 over Vs of t, which is equal to L2 di of t over L1 plus L2 di of t. Divide those out. So what do we know about voltage divider rule, if anything? Is there anything useful for voltage divider here? Well, the voltage drop on the output in this case, which is L2, is going to be determined by taking the inductance L2, dividing it by the sum of the inductances of the series circuit, and multiplying it by the applied voltage. Exactly the same as a resistive circuit. So voltage divider rule is exactly the same. And you can also expand this to current divider if you want. We don't have to go into a lot of detail. It's not, we probably will never use voltage and current divider, but I don't know if you were ever taught that in 111 or 112, but you can use voltage divider rule in capacitors and inductors, in farads or in henries, and get those ratios set up. You don't actually have to convert those to admittances, or not admittances, but impedances, and do the calculations this way. You can actually directly do it in DC and keep everything as a farad or as a henry. And it works perfectly fine. All right. Questions on that? Because that's going to be pretty much the focus. Yes, sir.
You say DIT, that means DIT over DT.
Yes, because I've been writing DI of T over DT so many times, I'm just trying to write it more efficiently.
And what do you mean by D of 0?
Pardon me?
What do you mean by D of 0?
B of 0? V of 0, this is the output. Looking across that capacitor. Pardon? Oh yeah, in this case, it's the inductor, it's VL2, yep. Either one. The reason why we say that is, let's see if our skills are mad. What is this? An op amp? What is my output? VL. How do you solve for the gain of the circuit? How do you solve for the gain? Pardon? Yeah, the gain of a circuit is defined as the output voltage over the input voltage. So how do you actually solve for V out over Vin? What are you just memorizing? So why I use V out is because a lot of times we're looking at these things as stages. So for those of you in your senior project design, you're looking at staging your devices and you're looking at the output voltage of a stage. It happens to be the same thing as the inductor or capacitor voltage, but it's just the output voltage. But let's do this. Let's see if our circuit analysis skills are really good. How do I solve for V out over Vin? First off, look at the circuit broadly. Everybody here has had electronics too, or some version of electronics where they have op amps. What type of an op amp circuit is this? Pardon? Not necessarily. It could be a buffer, but it doesn't have to be. What is a buffer circuit? Anybody know what a buffer circuit is? I think a buffer circuit is like this, right? No, it doesn't give you any gain. So the idea of a buffer circuit is it buffers, and I don't know if this is probably a term that doesn't really apply anymore, but it buffers the differences between two stages. So if you have a really weak stage for whatever reason, you want to try to provide some sort of a buffer or some allowance or slack between different stages. You put a buffer stage in between there. So what this does is this input here, the input impedance of an op amp is essentially equal to infinity. And the output has a really low impedance, call it 0. So what ends up happening is the power, the output that is determined from the circuit is all based on power from the op amp. So it buffers it, so it doesn't really, the incoming stage doesn't really have to provide any power to the next stage. And so buffer doesn't do anything to it. It just makes it 1. The output is 1. And it just, kind of slows things down a little bit for you, if you will. Okay, that's the reason why it's called a buffer. But this is an inverting op amp configuration. So what we need to do is we need to prove the inverting op amp. What's the gain? Let's check and see. What is the gain of an inverting op amp? What do you remember? Negative RF over RI. Does that ring a bell? How do you get RF over RI? Well, you have to understand a little bit about the op amp. And I gave you one hint. One hint already is, what is the input impedance to an op amp? This is infinite here, right? So how much current can go in here? 0. So all the current that goes here has to go here, right? Any current that goes there has to go and pass in through there. It can't go in that direction. But ultimately, what we're really focused on is we know that no current can go in. So let's not even include this part. We don't even need this part. So there's no current in. What is the voltage drop that is seen by the input and resistor, the RI? How much voltage is dropped over here? Well, that's the other thing that you need to have about an op amp. What do you need for the other op amp? I mean, for the op amp to operate. There's 2 things for ideal op amp. There's 2 major important things for ideal op amps. Infinite input impedance, and what else is infinite? How about the open loop gain? Do you remember that? Does everybody remember the open loop gain? Am I pulling too many? Did John not talk about this? Anybody?
No, you did.
What does the open loop gain multiply? It multiplies the difference between V plus and V minus, doesn't it? And that gives you our output voltage. So you take the difference in the op amp voltages, whatever that value is, and what do? You go ahead and send that to the output, multiply that by your open loop gain and send that to the output. If this is infinity, what does this voltage have to be to make sure that VO doesn't blow up? It almost has to be 0, right? It has to be so small to really counterbalance it to. So what that means is that this voltage difference between these 2, what does the voltage difference have to be between here? Has to be 0 volts, right? There can be no voltage difference between the plus and the minus terminal, because if there's a voltage difference between the 2, then you've got some major problems. So because there's no difference, that means that this connection, zoom in, this connection here, even though it doesn't exist, is basically a short circuit. It's physically not there in the real world, but the voltage has to be very small, so small that you could say that it's the same potential. How do you make sure that something's at the same potential? You set a short, right? You put a short. So what does that tell you about the voltage at this point right here? What does that voltage equal? 0 volts. So my current into my circuit, IN, is equal to my input voltage minus, what's the voltage on the other side? 0. We're going to divide that by RI. Okay. Yep, no, yes. So then any current that goes through here has to travel on and continue over here. How do you get current to go from your 0 volts point to V0? We get a plus to minus voltage drop here. So this current IN has to equal the current that heads through IF or RF. So that's 0, the voltage on the left side, minus the voltage on the right side, which is V0, divided by RF. So your final equation becomes Vin minus 0 over Rn equals 0 minus V out over RF. Those are the voltages that you use. So then we're ending up with Vin over Rn equals negative V out over RF. We do a little magic and we have V out over Vn is equal to negative RF over Ri or Rn. Is that what we expect for inverting op amp to get? Yeah, that's the inverting op amp game. So that is all based on doing our circuit analysis. Do you want to do one more? Is this good review or is it hurting your heads too much? Yes, sir. Sorry? Yes, VI and VN are the same. Yep. You want to do another one? Can I make what? I will try. Last time it didn't seem to make a difference. Maybe I can zoom in a little more. It's pretty well zoomed out. So let's see if I can zoom in. Maybe that'll make it better. All right, let's try 67%. Let's do one more way zoomed in. Is that too zoomed in? Let's do the other one. It might be a little bit too much. This is Rn. This is Vn. Oop. RF. And V out. So we're going to do the same thing. V out over Vn for a non-inverting op amp. What do you get? Isn't it 1 plus RF over Ri? I think. Is that what you said? Pardon? Oh, what did you say? I'm sorry. I thought you... Yeah, okay. So that's close. But remember, it actually adds a 1 to it. So let's go ahead and solve for that. Same exact concepts apply. We have a virtual short between these two. So we're going to go ahead and say my input current is equal to VI minus 0 divided by my Ri. That's my input current. Okay. Now I continue on. And this current here is, let's see, am I doing this right? I think I'm not doing this right. Let's continue on. So that's equal to V out. Whoops. 0 minus V out over RF, but I don't think I'm doing this right because it's it should be non-inverting. What is this do I have my non-inverting op amp set up correctly? Let me go ahead and do this real quick. Wrong one. Sorry, I'm getting used to another new computer. That's a voltage follower. Okay, here we go. So I put the wrong connection. You can see here, Vn is at the positive terminal. So that's incorrect. So let's go back to this one. So this is sorry, I haven't done this in a while. This is ground. And this is VN. Try that again. Okay, have I got that right? So yes, yes. Got it. Okay, so this is the non-inverting configuration. And I'm trying to prove this here. So virtual short still applies here. As long as your op amp isn't saturated, you're going to get that terminal here. So what that tells me is the current is going to go in this direction because that's assumed to be at a higher potential than ground. So my current through IR1, IRN I should say, is going to be equal to V in minus 0 divided by RN. No current can enter or exit the input terminal of the op amp. So all that current has to come through here. So that current is going to be V out minus V in all over RF. Okay. So now I'm going to go ahead and simplify. So I have V in or VI, either one, over RI is equal to V out over RF minus V in over RF. I'm going to collect the VNs. VN times 1 over RI plus 1 over RF equals V out over RF. Now I need to go ahead and solve for V out over VN. So V out over VN is going to be equal to RF divided by 1 plus RI plus 1 plus RF, common denominator. And then I'm going to invert and multiply. Let's see. Invert and multiply. Am I doing something incorrect here? So I invert and multiply, I have RF squared, which I definitely don't want. Let me do it back over here to simplify it here, because I might be doing incorrect algebra. So let me do one more step over here. Whoops. So this is Vn times Ri plus RF over Ri plus RF equals V out over RF. Okay, that's what I did. I inverted on the wrong side. So then V out over Vn is equal to RF times Ri plus RF over Ri times RF. So this is RF. I'll cancel an RF and then I end up with Ri plus RF over Ri, which is equal to 1 plus RF over Ri. That is how you derive the non-inverting op amp. And as next semester, probably we'll spend more time looking at different configurations where we actually put capacitors in there, because we can do some things with integrators and all that stuff, but that'll be the focus. Okay. All right. So that is the end of section 3-5. We have a couple more sections to go, but that is the end of what will be on your first exam. So exam number 1 will be a week from yesterday. Covers all of chapters 1, 2, and 3. What do you think? So what I'm thinking is on Thursday, we'll do sort of a review. We'll go over, answer any questions. If you have any problems on the suggested homework that was given, we can try to do some of the suggested homework problems and go from there. But that would be the idea, is to just do that. So if you can do the homework inside out, backwards, forwards, you should have no problem on this test. It would be very similar to the homework problems, the suggested homework problems, and the ones we did in class, because it's all the same material. Yes, ma'am.
I was wondering if you could post the solutions.
I don't know if I'll be able to get to them anymore because my computer is not operating correctly. So you do have the answers in the back of the book. So if you have a problem, yeah, because the book is out of date, you can't get solutions anymore. And I used to have all the solutions, but I don't actually have access to because I had a hard drive that was working and that crashed, and then I haven't been able to recover that information. So I'm kind of a little bit out of it in terms of the material. I've just been having a lot of computer issues. But I think if you want to practice the problems, get the answers, if you're struggling to get an answer, you can go through some of those problems for sure.
You said they were in the back of the book.
Yeah, so if you look at the end of each chapter, I have what are called suggested homework problems. And there's a lot of them, so you can just take a look at those suggested homework problems. And those will give you a pretty good idea of the type of problems of the test. And if anybody doesn't have the book, and if they want to take photocopies of my stuff, just let me know. That's perfectly fine. We can make that work. Okay. Any other questions? All right, let's just do a couple things on transformers. We're not going to worry super duper about mutual coupling. We're just going to look at a transformer and understanding the basics of it, because it is a pretty important device for us. And a transformer is really just a fancy inductor, because if you recall, how do I build an inductor? I've got a magnetic field that's being produced by a current. So a current carrying wire is in here, and you're producing a magnetic field, and you only use a piece of iron in the inductor to sort of allow it to be bigger. So if you look at, flip this back. If you look at air core, you can see it's just a piece of wire wrapped in a pretty good circular motion. And inside the core is where you have a concentrating magnetic field. Does that wire look bare? Looks bare copper, right? So who's to say, why would the current go through this wire? Why wouldn't it just go right through here? Because it's called magnet wire. And magnet wire is exactly for that purpose, is for creating magnets. The voltage drop between, let me see if I can zoom here. The voltage drop between this coil and this coil is very, very small, maybe a couple volts. So for magnet wire, all magnet wire is, if you can't really see all that well, it's basically just copper wire, super flexible, but it's got a super, super thin insulator on it because it doesn't have to insulate for very much voltage. I don't even know if this one even tells you what the insulation is turn to turn. It might not even say, because it's so little. It doesn't need to have a very high capacity because the voltage across it is not that much. But if you look at standard inductors, oops, I can't type today. You can build them here. So hard to see, but you can see that little yellow piece right here. That's a piece of metal, usually steel or iron. And the idea is you wrap this inductor around a piece of iron because it's going to concentrate the flux. So if we go back to this figure here, we have a magnetic field. Let's just take a look at an inductor that'll generate all kinds of magnetic fields in any direction that it wants to. Because air is not that bad of a conductor for magnetic energy. So if we talk about magnetic materials, so we can look at see if this table here. So we want something to have a relatively high permeability. Permeability is the same thing as saying conductivity. So we have a conductance of a wire. Permeability is how conductive something is to magnetic energy. And if you take a look at these elements, you can see iron has a permeability of 200,000 times air, which is pretty good, but it's not outrageously good. If you compare the conductivity of copper, it's like 2 × 10⁸ or something like that. It's 20 million times better a conductor than air is. This is only, and this is pure fancy metal. Most of the time, if you look at it, you're probably in the 5,000. Like this one is 99.8% pure. That's only 5,000 times better conductor than air. You start getting into some really elegant material. These are super duper high. Like I don't even know what met glass is equal, is whatever that is, but that's a pretty fancy, rare magnet that has a lot of capacity. So think about your car antenna. What is your car antenna picking up? It's picking up magnetic energy, the waves that are being emanated from another antenna, and they're traveling through. So in this circuit, there's magnetic energy that is all around, but you want to concentrate it. So if I have a wire that's wrapped around a piece of iron that's 5,000 times more conductive than air, then we're going to focus our magnetic field inside that core or coil of that magnetic core. So a transformer, if you run it open circuit, it's just an inductor. That's all it is. It doesn't do anything. It acts as a big old inductor. It can act as a filter. It can do whatever it needs to do. So it's an inductor. What changes it is when we put a secondary set of wires on there. Because this flux, we're going to say that it exists everywhere in that core. And it's basically the equivalent of a current through a wire. That magnetic flux exists everywhere. And so what happens is, remember how we generate a voltage? VL of T equals L di dt. We're going to generate a voltage here. So our voltage that is across here is primarily because of the inductance here. But we're also going to generate a voltage on the secondary side, so I'll call this VLS, is also equal to that changing current that's through here. And what they do is magnetically, you have a circuit that has a voltage here. So this is, we'll call this primary. That this is because of the LP. And we also have something because you have some mutual inductance between there. So this is a transformer whose voltage is determined by two things. It's determined by, so this is IS and this is IP. So its voltage across it is determined by the self-inductance of the coil of wire on the high side, as well as that mutual inductance. So what that means is that if you have no current over here, this has to make up the entire difference of your circuit. If you have a lot of current going through here, then this is where you get most of your voltage drop. And that's how you move power through your transformer. You're moving power through the transformer because you increase the amount of load, the IS of T, you're actually going to increase the amount of power that is conveyed. So how do you make a transformer work harder? You just put more load on it, meaning you allow more current to be pulled out of the transformer. That's all you're doing is you're working it harder. And that's going to essentially make this term dominate. It's going to be a higher and higher percentage of the element that's going through there. And that also is going to drive this, because this, as I pull more secondary current, my primary current also has to increase to be able to make up that difference. So now this voltage here gets to be higher and it pumps out more energy, and that's essentially how a transformer works. Yes, sir.
Does that efficiency of the transformer differ if you're trying to like step down or step up the voltage? Or-
So good question. Does the efficiency of the transformer change? The efficiency of the transformer doesn't change. In an ideal transformer, there's no resistive losses. So it doesn't matter how much up or down you're going, as long as all that magnetic field stays within the core of the transformer and gets fully what they call linked, then efficiency doesn't change. So that's the nice thing about transformers in the real world. Transformers in the real world can go in either direction. I can take power and go from low voltage to high voltage, which is most of the time what generators are. But the generator that's outside the window right now, that's probably running at 480. But you could step it up to transmit power all through campus at 4160. Or if for some reason it was connected to a motor, or you had to pump, water for it somehow, and you had to go in the other direction, the transformer that it connects to could go in either direction. So no efficiency loss, no differences. Doesn't matter if you go up or down. And you can go up and down in almost unlimited ranges. You can go from, the biggest ones I've seen is 13.8 kV to 345,000 volts. That's the biggest step change that I've seen, but they might have bigger ones when you go out west. So the ones I'm talking about is the generators. Some big generators and some medium-sized ones operate at around 13.8 kV, and they'll oftentimes will step up. If it's a big enough generator, it'll step up to 345. So you're going up to, what is that, 20, 30 times the increase in voltage. And at that point, it's just the number of turns. So how do you step up the voltage up or down? You just have more turns. So this is going to say the number of turns times I on the primary, and then the number of turns times I on the secondary should be the same, because there's something called magnetomotive flux, which is what's going to drive that voltage, that mutual coupling. So all you have to do to step up or down is have more or less turns. That's how a transformer works. Literally, it's just a couple inductors that are on a common coil, and their flux is being linked. So what is seen on one side gets seen by the other, the flux, and then that's how you transfer power. So there's no efficiency loss, because a transformer, it transforms energy through a magnetic circuit. And how much power is consumed in the magnetic circuit? None. Because it's all magnetic energy. Power is I squared R. It's not flux squared. So that's why you can have an antenna at the top of Sugarloaf Mountain, right? I mean, TOS, for those of you who listen, and it says it's 50,000 watts of power, but it can move 50,000 watts over a very large distance. We're moving 50,000 watts for electrical power, with electricity. That's noise. Main Independent Station is 550 megawatts. So they're 50 kilowatts or 0.05 megawatts. And at Main Independent Station, you have 1,000 times more power. And in Bangor, Maine, the load in Bangor, Maine is probably 50 megawatts peak load. So that's because the power consumed is much higher electrically than it is magnetically. So a lot more losses in electric systems. That's why people here have their smart chargers. Anybody here have a charger that they just put on a desk and then you just put your phone on it? Why does it work? Why isn't your skin burning when you pick it up? It's coil to coil. Yeah. So there's no electrical energy that's being lost. I mean, there's a little bit in the air because that magnetic flux travels away. So it's not as efficient as a hardwired one, but there really hardly is any power loss. And that's one of the things that they've talked about with the military is transferring power. You can use microwave, where if you can line things up perfectly, you can actually transfer power magnetically over pretty great distances without a lot of losses. But the problem with that is if a bird or something walks, flies in the path, if they pick up that magnetic energy, it'd be pretty strong. And it's also not practical too, because to move a lot of energy, you would need a very wide area or a very highly concentrated magnet. So that would not be practical. Ali, did you have a question or a comment?
Yeah, I was just thinking, can we, like, is it possible to make a transformer with like a super wire and something like made of like metal?
Yeah. Yeah. So the question is, can you make a transformer? You can take your pen and make a transformer. Because air is not a terrible magnet, right? It's not great, but it's not terrible. So you can have what are called air core transformers. You have to drive a lot of current to get that to work. But yeah, normally you would just take a piece of, you could actually go, if you really wanted to try something, go to Home Depot and buy a couple of washers, just steel washers, and take, 5 or 6 larger ones and sort of just glue them together with some sort of an epoxy, a thin epoxy. Then let it dry and then wrap one side with a bunch of magnet wire and then go completely on the other side, not touching at all, and do the same thing. And you just built a transformer. Because the washers are usually made out of steel. So that would not be a terrible transformer.
How many turns do you probably have to make in order to like generate the magnetic field?
So the question is how many turns? You only need 1 turn to generate a magnetic field. But if you want to make it so that you don't need 10,000 amps to do anything, if you have quite a few turns, 500 turns, you can get down in the milliamp range. So for those of you thinking senior projects, if you want to do coil guns or rail guns, you sometimes have to just figure out the amount of magnetic energy. And that's going to be dependent on the number of turns that you make. Because the more turns, the less current, because it's all magnetics. And the magnetic energy is dependent on the number of coils times the current. Okay. And that's basically how you get what's called the turns ratio. So if I have a transformer here that goes from, we said 13.8 to 345, very simplistically, you could say this one has 13.8 thousand turns, and this one has 345,000 turns. There's more to it than that, but that's how you could actually make it work. All right, so don't forget, a week from yesterday, your first test. Hopefully I have less issues with technology. I apologize. It's never had so many issues, but that's all I had, unless there's any question from TV land. All right, thank you very much and have a wonderful day.
Thanks, Paul.
Thank you.